Okay, today we're going to go through a little bit of history and some basics to sort of understand how the idea of electricity was developed. And the first topic we're going to look at is static electricity. And we've probably heard stories over the years saying that Benjamin Franklin was flying a kite during a lightning storm, so he discovered electricity, or Thomas Edison invented the light bulb, so he must have invented electricity, or Alessandro Volta made the first battery, or Nikola Tesla made alternating current, and the list goes on and on. All of these people helped harness energy and use electricity, but they never eventually discovered electricity. The first mention that we know of by written account is the Greeks. So back in like 600 BC, the Greeks found static electricity to be more of just sort of something that was cool or amusing. They would rub a chunk of amber, which is just a hardened sap, so just a yellow kind of thing. It looks like the mosquito things on Jurassic Park. That's amber. So they would take that thing, they'd rub it with fur or something, and then they would notice that it would become statically charged, and they'd be able to pick up dust, leaves, anything like that. So what they saw, what they experimented with, is what today we call static electricity. And they had no scientific explanation or rationale behind it. They just thought it was interesting. But what they did realize is if they would charge two objects, so they would rub two pieces, sometimes they would get them to repel. So if they took two chunks of amber, rubbed them both, put them next to each other, they would separate on their own, which is key to electricity and static electricity, as we're going to see in a few minutes. Later on in the Middle Ages, so we're moving quite a bit ahead, so we're in the 1600s now, William Gilbert was a guy that tried to put some sense to the electricity and static electricity that the Greeks were describing. So he wanted to come up with some sort of theories, and he was actually the first one to coin the word electric. And electric is basically just a variation on the Greek word that they used for amber. So that's kind of how that came about. He had some sort of success, but his key idea was that magnetism and electricity are different. Up until that point, most scientists sort of thought they were the same thing, just sort of different versions of each other, but he said that a magnet's always a magnet. Once you have a magnetic piece of iron, it can always attract particles. But electricity, we had to rub the amber rod to make it have an electricity static charge, and eventually would wear off, where the magnet wouldn't. Later on, so now we're in the 1700s, Benjamin Franklin this is about the time when he started getting involved. And according to the stories, he did indeed fly a kite, but he didn't fly it on a lightning day. He was just trying to figure out if there's any kind of electric charge in the air. Others have done that, so other scientists tried to fly their kite in a lightning storm, but they were all killed. And another interesting story is Franklin typically would get his son to do all the experiments while he'd just stand back and watch. So even if there was some sort of mistake, it probably would have been his kid that got killed and not him. So anyhow, what Franklin did find out was the electricity is basically just a discharge of static electricity. And then he was the first to sort of start coming up with the ideas of positive, negatives, and so on. So he would take a chunk of amber and he would charge it, and he'd have it hanging from a thread from the ceiling so that there was nothing touching it. Then he would charge another piece of amber rod, and he would move it close to it, and he would get them to repel or move away from each other. Then he found that if you rubbed a glass rod with silk, it would do the same thing. So he'd have a glass rod hanging there, he'd rub it, put a charge on it, rub another one, put it close together, and they would also repel. But then he found if you put the amber rod and the glass rod near each other, they would attract. So he found that the two amber ones repelled, the two glass rods repelled, and the one of each attracted. So he figured the charges must be different, and he just decided for no particular reason, he just come up with a name, and he knew they had to be opposites, so he said the glass one was positive and the amber rod was negative. They could have been the other way around, it could have been something totally different, but that's what he went with, and that's what's pretty much stuck ever since. He also tried to come up with the idea of why there was these positives and negatives and attracting and repelling kind of idea. And his theory, which isn't accepted today, but it kind of was the basis for what we do use, he sort of thought that every object is made up of a fluid, and he called it an electric fluid. And he thought that everybody's electric fluid was positively charged. And if you had too much of it, then you were positive overall. If you had not enough, then you were negative. So he sort of used this idea of you should have a certain amount to be neutral. Anything more was positive, anything less was negative. He backed it up with sort of saying that you could charge an object, you could like create a charge on one, and then what that showed was a deficit on the other. So he was sort of coming up with the idea of like if you rub a balloon on your hair, you're moving electrons from your hair to the balloon or vice versa, so one becomes positively charged, one becomes negatively charged, but the balance was still the same. And that was kind of the key idea to his fluid theory, is that the balance was always the same. We're just shuffling from one to the other. So although that's not right, it did lead to what we use today, which is the law of conservation of charge, which means the net amount of all electric charge produced is going to always be zero. So we can have positive and negative interactions, electrons moving back and forth, but the idea is the total net result is still going to be zero. So we can't create or destroy charge. All we can do is move them around. So since that time, so in the last 100 years or so, it's now, pretty much accepted knowledge that it's not based on some sort of fluid, it's based upon the makeup of the atom. So we know that our nucleus is made of protons and neutrons. The protons are positive, and it's surrounded by electrons in orbit, and in the normal state, the protons and electrons balance out, so we end up getting a neutral charge. But we also know that we can add or lose electrons from the atoms, which would then create it to be an ion. So if we lose electrons, it's going to be positively charged. If we gain electrons, it's going to be negatively charged, and so on. One quick question, or one kind of thing to think about, is normally when we get static electricity, it only seems to last for a little while. So if we rub our hair on a balloon, stick it to the wall, we wait, it might last an hour, it might last 2, or whatever, it might not last too long, and eventually it falls off. So the question is, where does that charge go? It doesn't just disappear. We already say the total charge can't be created or destroyed. It just gets shifted around. So what ends up happening typically with static electricity is the excess charge leaks off into water molecules. So for example, if you have excess electrons, those electrons are going to get attracted to water molecules, which typically are positive on one end, negative on the other. So they start sort of collecting on the positive end of the water molecules. So eventually the object will lose charge and become neutral over time. It also sort of the idea of grounding, right? If you have a grounding rod or you touch something, that'll balance it out. So that's why when you shuffle your feet on carpet and you touch a doorknob or whatever, it'll spark. That's basically just that excess charge leaking off or neutralizing. In terms of water molecules absorbing charge, it's sort of neat that we typically get more static in winter. If the air is drier, the electrons, there's not enough moisture, so the electrons aren't picked up as often. Therefore, we tend to get a little more static in the wintertime. And that's it. So that's it for the theory. There's not much in terms of calculations or anything. We're gonna get to that in the next couple lessons.